Perfect. So I will move to another part of the presentation of the session, and there we will look to energy storage applications by having examples, what are the pro and contras, and so on. Fast charging cooling, I will look to that. Recycling and end of life. And finally, last but not least, to make it complementary, we will have also a look to hydrogen. And by the way, if there will be any question, just stop me accordingly, then we can discuss that. Now, again, everything starts here. As I mentioned, just as a repetition, electrification is increasing. There will be a number of, over the coming years, numbers of the vehicles which will be more electrified. We are moving away from conventional vehicles due to emissions reasons, regulations, and so on. And electrified vehicles, either battery electric vehicles or fuel cells or plug-in hybrid electric vehicles, are going to gain more and more the market, and that's also what is reflected by the yellow line. Please take into account the yellow line will be on the lower side or the higher side. The future will actually tell us what will happen in the long term. But based on the news that we are getting from the market, that many OEMs already decided by 2030 they will completely stop with their conventional platforms. And that means that batteries are going to become very important, in particular for the transportation, as we explained during the first session, which is indicated by the light yellow bars. And that the market at this stage is dominated by China, and Europe is trying to catch up with this technology, with this strategic technology. Now, what does it mean? That means, in terms of application, we know, of course, passenger cars is very important, as it was explained during the first first session. However, we see another market which is growing over the years is the electrical buses. And the electrical buses, typically battery electric, and we see here the differences. These graphs illustrates actually over the years how the battery bus market evolution was worldwide between Europe in blue, maybe you don't see that, but it is this one, blue, and China. So in 2016, the production, the sales per year in China was around 116,000 buses, compared 341 buses in Europe. And then how it happened? It happened actually, the increase was due to strategic decision from the Chinese government to give high incentives in order to attract the market. And when the market started growing, then they start reducing the incentives, but still the market was powerful to continue independently. This is something very important because knowing that the capacity of batteries are typically for buses are in the range of 200, 300, 400 kilowatt hour, which is making actually a strategic market. And there are quite a lot of bus manufacturers in Europe, like Volvo, Irizar, VDL, MAN, Daimler, or Mercedes, and so on, which are active, or Iveco in this field. But nevertheless, still the market in Europe is very small, and that's what is actually indicated below, that 98% of the market share is in China. Shenzhen city in China has already 16,000 electrical buses, only one city. So that's one type of application which is gaining quite a lot of interest, a lot of focus these days, and we see by also the increasing orders. Now, when we speak about buses, we have also to speak about the requirements. And buses, when we speak about requirement, typically it means how we are going to use the batteries accordingly. And there are different scenarios to use batteries in electrical buses, either by swapping the batteries, as we call it. And what does it mean, battery swapping? Changing the battery every time when they are empty. Typically, that is around 3 to 8 times that you are replacing the batteries, and the capacities are between 50 to 200 kilowatt hour. Or another scenario will be that charging the battery at every bus stop. That means to keep the battery capacity very small, but you are charging them often. And that means also your charging infrastructure should be foreseen for that, or charging at final destination, what we call it depot. And the battery capacity is quite not so large as this one, but still large enough. Or another scenario which could be is having larger battery where you charge that just once per day. Now, what is idle situation? There is no idle configuration. Everything is depending from one city to one city, from one strategy of car or bus manufacturer to one manufacturer, what types of infrastructure is available, what not, what are the regulations associated with that city. But typically what we can say that those two aspects are very high. Why? Because you have the operation requirements here are very tough, and here the charging infrastructure is not very cheap, knowing that for every kilowatt charging, you are paying around something between 700 to 1,000 euros. And that means at least a couple of things that you have to take into consideration. So different scenarios that are associated. Now, beside buses, we have also the truck market. The truck market, we have typically 3 classifications of trucks: urban trucks, regional trucks, and long-haul trucks. What are difference between them? Are typically urban means 100 kilometers distances. Regional trucks up to 200 kilometers. Long haul, I would say plus 500 kilometers. And we see here, depending of the regions that we have, that Europe is quite well more advanced than US and China in the electrification of long haul or heavy duty trucks. We see that regional trucks are getting higher intention, and the urban ones, the electrification, while the long haul will never become electric. What it's going to become, it's more actually to become more hybrid to such extent. And you will see in the later stage, it will be more and fuel cell or hydrogen oriented than something else. So this is a market in Europe which is growing quite fast and has a lot of potential, because the key player in the world are still European, like DAF, MAN, Daimler, Volvo, Scania, etc. If we look to the American market, we see, situation is different. Expectations of the first electrified are expected by 2025. And we see in China, yes, even it's foreseen for the longer terms, starting somewhere by 2028, 2030, to be more in the electrified, and even not for all, it's only for regional and actually urban one. So that's something that we have to take into account, and that is also bringing me to this message, that this reason why the transportation for passengers, buses, trucks, and so on is going to gain a lot of mark and will require a lot of batteries. If we look further to further applications are scooters. You know, we have two-wheelers, we have three-wheelers, we have bicycles, we have steps, different mobility modes that we have are facing now on our roads, and that are aspects that we have to look to it that carefully. And that are typically the best way is having them electrified and preferably battery electric, and there are different ways to operate that. Or either you charge them from a dedicated locations, but also what we see more attractive model is by having such types of charging, battery swapping, and locations, logistical areas where you can bring your empty battery, plug it in, and then to take a charge one, and you pay actually for every used battery accordingly. The interesting one, because you don't need to foresee additional infrastructure, you don't to do a higher investment, and it's creating quite a lot of flexibility. What is important that the battery format or the size should be quite standardized what can be offered here, and that's the only issue. But it's a perfect solution for fleet aspect. It can be used for three-wheelers or four-wheelers, depending what the needs are. Electric vessels. Electric vessels, as you know, due to regulations, regulations are not only imposed on the automotive industry, but also the marine is suffering from the regulations. So the CO2 should be reduced quite a lot. And we see more and more for smaller and medium vessels, a lot of electrified vessels on the in the meantime on the market. And here, electric or battery electric is the most preferred solution. And if our bigger vessels, hydrogen-based are the best one. What does it mean? Of course, here we don't speak about such small batteries. We are here speaking about megawatt hours batteries that should be implemented, and which are actually container size, 40 feet container size, that you have to think about that, and that are charged either conductive or inductive in a different way. Good. Further, we see even off-road application or vehicles get electrified. CAT, the first one in the world, start electrifying an excavator. That is something that we have to take into account. So something quite big market there worldwide, because you see that everywhere, and they are one of the contributors of typically the conventional one of high emissions, and by electrifying them, you can reduce a lot of noise from one side, but also the emissions. So here, again, we are speaking about large battery capacities in terms of 400, 500, or even 1 megawatt hour battery capacities. Another application, off-road vehicle, big trucks, 45 tons mining trucks, which you typically use in Australia and in other places in the mining industry, which are fully electric. Becoming fully electric, they start with hybrid and then they went to fully electric, and they have typically a battery capacity which is not small, 1 megawatt hour. 1 megawatt hour, it means a lot of tons batteries that they have with them in order to make that possible. Now, it's not only in the automotive industry the batteries are can be used, but also even in the stationary industry can be used. So here, on this slide, you see the different groups of stationary application where battery can be used. Group A in the electric supply, where you typically have electric energy time shift or electric supply capacity, or in the ancillary services for load management, area regulations, voltage support, grid system for transmission support, etc., and even for end user or utility customers where it can be used, or even for renewable integration. This is quite a tough market. However, I want to emphasize again that this market, which is represented by the green bars, are very much smaller than the yellow one. And that's something that you have to take into account. It's a growing market, but it's quite a small market in general. But this also needs quite a lot of energy in order to support that. Another aspect is the fact for every application, you cannot have the optimal solution which contains the power and the energy. And hybridization for stationary applications could be a solution by hybridizing those technologies which have high power with this technology which have high energy. Why? Because for those applications, typically space and weight is not a problem, like in the automotive industry. So space and volume is not a problem. So you can easily do that by smart integration of high energy lithium-ion batteries, like with electrical double-layer capacitor, through smart power electronics like DC-DC converters. Any questions so far regarding the topic which is related to applications?
Any questions for the market or applications? Not from...
Okay.
No.
Great. In the first session, someone asked second life. Second life of battery, what is firstly second life? By law or by standards, we are assuming a battery end of life when the capacity is reduced from 100% to 80%. When it's 80%, we typically assume it's end of life. However, it's just a standard definition and not a regulation, but end of life can be even 70% or even 60%, depending how you are fixing your conditions. Nevertheless, consider 80%, and then there are different scenarios, or you bring the battery at a recycling plant, like the Immersion one in Belgium, or you do some modification where you can bring that afterwards to use it in another type of application. And possibly such applications could be a potential application for second life applications, even scooters, because the requirements of them in automotive, the requirements of them are much lower than the automotive one. Concretely, what does it mean? That second life market is increasing. It has a lot of potential. However, there is a problem, and its problem, firstly, is financial problem, but you will see also it's a regulatory problem. We know that battery prices are going to drop and drop quite very fast. Now we are in the range of around 1,100 euros per kilowatt hour at pack level. And the long term, it should reduce to 70 euros per kilowatt hour. If second life battery cost is not below 50 euros or dollars per kilowatt hour, I personally don't see any business models in that regard. Why? Because there will be each time an argumentation why to use a second life battery which is less reliable than a new one with a cost difference which is so small. So that is uncertainty that we have in that regard, and it's a price issue. Second aspect is, as I said, we have an automotive battery. You get it in a vehicle. At the end of life, you dismantle that. You take it out, and then typically, in order to use it for second life of applications, you have to go dismantled on the level of modules. And what typically is happening, or you send that to recycling, disposal of batteries, or you do refurbishment, changing of dedicated aspects. The rest maybe should be adapted. Some parts and are in bad quality, should be replaced, etc. And that's where you can use it in station applications. And that process of inspection, dismantling, inspection, and manufacturing again is actually indicating that the cost will be each time much higher than $49 per kilowatt hour. And that the difference between second life battery and new battery will be quite dramatically small. Very small, which is making this business model quite not very attractive. Secondly, I mentioned that the stationary market in green compared to the yellow one is very small. The indication that the amount of batteries which will be available for second life potentially will be much more than what is actually required for second life. So what does it mean? That in any way, many batteries will go directly to recycling in any way. There is no discussion about that. And some of them potentially will go to second life. However, the business model is not clear at this moment. But we know that the market potential is there. So by 2035, we are expecting something around 11 gigawatt hour annually for second life batteries, and which mainly will be used for home storage, grid energy balancing, and also for applications like UPS, vehicle to building, etc., where typically requirements are much lower than the automotive one. And we see on this graph the evolution that cumulative second life battery capacity is going just to increase the coming years. So we are producing more and more electric vehicles. At such a moment, after 6-8 years, the battery should be replaced and they will be available for second life batteries at that moment. So this market is potential, I would say, of this market is there, but the business model should be quite okay with that. Now, then over Europe and worldwide, there are quite a lot of projects that has been done recently, but also in the past, like Vattenfall, BMW, and Bosch. They were just testing what is possible, what is not possible, how the further modification should to be, and so on. And they have implemented different types of concepts worldwide. And recently, even in the Spain region, in the Basque country, Eléctrica used a second life batteries for stabilizing of a charging station, electric charging station. So there is a lot of potential there. But it's still, the business model is not quite clear. So it is still a technology which is under demonstration phase. As I mentioned to you, the cost is an important fact, since we are expecting that the battery cost will drop further due to mass production that we have, as you can see here, and due to the increase of the energy density in the same volume. What does it mean in general? That the pressure on second life batteries will become very high, and from that perspective, as I mentioned, the business model is not straightforward. Another problem of second life batteries is much more related actually to state of the battery. You consider you have a battery which is end of life. You are taking from electric vehicle, from car manufacturer like, I don't know, BMW, Volkswagen, whatever, but they don't offer you the data about the first life of the battery in order to see what is the state of the battery in a proper way, in order to make an assessment where if the battery is good or not, or where it can be used. From that perspective, that is which we call lack of data, of transparency of data, which car manufacturers are not willing to share that often. From that perspective, a state of health estimation is a key element in that regard, which you typically don't get the data from the car manufacturers. And one way to deal with that is by applying methods to estimate the state of health. And here, that I just combine them for you in 3 categories: the experimental methods, model-based methods, or machine learning methods. However, independent which method that you select, there is one problem. It's a time-consuming method. It takes time. It cannot be done in a couple of seconds, of minutes. It takes a lot of time, and that is making the logistical process of Second Life state of health estimation very difficult. That's also a big bottleneck. Secondly, as I said, our manufacturers are storing all the data in their BMS, and they don't give access to this BMS to get the data from there. Second aspect is typically any BMS for an automotive industry is designed for 10 years. It has a reliability of 10 years. What does it mean 10 years? After 10 years, you are entering in a position with a reliability which will be much lower. So from that perspective, you have to know when you go to Second Life battery, typically all BMS should be modified or BMS should be replaced. And that is also increase of a dedicated cost that you have to add on the Second Life batteries, which makes the indicated cost of $49 per kilowatt hour quite very difficult. Then, as I mentioned, there are numbers of barriers, and I summarize them actually in 4 points. The first 2 points are about economic uncertainties. We don't know what will be the cost of a new battery in the coming years. If the cost will decrease, follow the trends that we saw in the last figures, the last slides, then the pressure on the Second Life batteries will be very, very heavy as well. Secondly, is a complex and adverse regulatory structure. Consider, what does it mean? Consider you have a battery which you take it from electric vehicle, and the car manufacturer at that moment is the owner of the battery. You get the battery from the car manufacturers and you use it in another application, or you sell it for another application. Nobody knows at that moment who is going to become the owner of this battery. Is it the OEM or it's a new owner? That's also a complex regulatory structure that we don't know. I mentioned liability concerns. Who is going to be responsible for that? Is the industry leader? Is a new owner, because there are obligations in terms of insurance, reliability, etc. Lack of data of performances during the first and the Second Life application. That should be also very and it's a problematic. So solution should be to make all this data available in one or another way. So from that perspective, if we summarize everything in one or another way, we come to this graph. There are a lot of numbers of uncertainties in terms of Second Life batteries, in terms of economic point of view, and in terms of reliability point of view, complex regulatory structures and battery data and so on, that at this moment, the business model of Second Life battery is rather vague and unclear. By 2025, it will be much better by adapting the regulations, the processes behind the framework structures in order to make that possible, also by gaining a lot of experiences for demonstration sites. So that is what is related to second life batteries. Perfect. Then we will move to the cooling. Now, these graphs explain quite a lot of things. And our lovely Europe, we have quite diverse climatic conditions. In the winter, it can be quite cold. In the summer, it can be quite very warm. And we have quite very diverse temperature or climatic conditions compared to Asia and other places. What does it mean? That in the winter, we need that vehicle, even battery, should be warmed up, heated, and the summer it should be cooled down. And of course, from a vehicle perspective, or even any other which application it will be, we want to have a modular concept which we can apply it in Sweden or in Spain or Portugal, whatever. So from that perspective, in Western European countries in general, based on statistics, we know that around 60 to 70% of the days we require heating. In the more you go to Scandinavian countries, it's becoming worse. Of course, the more you go to south of Europe, it's getting, it's another scenario. But nevertheless, more or less, 60 to 70% of the days of the time we need heating. So heating is an important one. And for once, for people that doesn't know, heating is consuming more than cooling. So something that we have to take into account. And that is also one of the design parameters of a battery system. Since heating is consuming, you have also the energy that is needed for the heating to integrate that as a sizing of your battery pack. Nevertheless, when we speak about thermal management, or cooling, we can look at from different ways, in particular when it is about fast charging. We have air cooling, which we started with, Nissan Leaf, which is based on natural air convection. And what does it mean? There is no any specific ventilator. And that's the reason why when Nissan Leaf was first time integrated in Arizona, they start failing very fast because it was just blowing, the air was blowing at 45 degrees. We could have also air cooling by forced air, like in Toyota Prius or Renault Zoe. Or we could have liquid cooling by indirect liquid cooling or direct liquid cooling. Direct liquid cooling is like the immersion cooling, and then we have also cooling by refrigerant, or we could have also passive cooling technology like phase change material. And last but not least, we have also the hybrid cooling, which could be combination of different solutions. So what is the optimal solution? Optimal solution is depending on the application. But of course, if we go to fast charging, I can tell you air cooling will not work. Then liquid refrigerant cooling has some limitations. Liquid cooling or typically most the preferred one. Now, what does it mean? In a vehicle, you have limited space and the weight should not be high as well. And everything is about 3 parameters: packaging, cooling capacity, and the battery output. So here, that's things you have to take into account. The packaging should be compact as much as possible because the volume that you have is limited and the cooling capacity should be high and particularly. So what do we see here for electric vehicles and particularly and plug-in hybrid electric vehicles? We go away from passive cooling towards liquid cooling anyway. There is no another way. And here, and then if you go, of course, to more fast charging, you go more and more to direct cooling. That is aspect that we have to know, and that we have to take into account, which is also one of the key design parameters. If we simplify that simply, this complex picture, this one, we see actually that passive will be passed, active air cooling will be passed, and we will just go in this direction. And here are just exploratory solutions that nobody knows where we will be. Now, what does it mean? What is air-cooled? What is liquid-cooled? What is direct-cooled? And that is actually indicated here. Air-cooled, passive air-cooled is actually, you have ventilator, you are blowing air from one place to another. But it can be also blowing fresh air, which could come from the HVAC system that you have from your cabins. That's also like the way is using. Also, it can be optimized fresh air. So actually, passive air cooling, sorry, it is just an outside temperature air that you are flowing through the battery, and air cooled is the acclimatized air that is typically coming from the cabin, which you blow through your battery, but which you cannot control too much. Liquid cooling is, of course, much more complicated, where you have a closed loop system, primary and secondary loop, where you have typically a chiller, a radiator, condensers, and you are regulating that accordingly in order to cool the battery through heat exchangers and to keep the battery in the right temperature conditions. Or direct cooling, as we discussed before, where you have a direct cooling, which either could be through contact with the cooling plates or direct cooling with the battery cell. So different solutions. One is much more complex than others. One is much more costly, and it requires more or less volume. What is the motivation? The motivation is we want to keep the battery at the right temperature window to avoid problems. That means to avoid problems, to avoid degradation, and to avoid thermal runaway. So, and preferably the temperature between the batteries should be uniform as much as possible, as we explained before. What does it mean? And if we do that, then we will have almost a perfect solution, and definitely not what we have here, imbalance between the multiple battery cells. And by keeping also the battery in the right temperature condition, as you see here in the green one, we could have less agings, also longer lifetime, and also safety. So the effect of the temperature, I think I explained that very before, it is quite clear, is to keep the temperature distribution quite equal, homogeneous, but also that the temperature could be kept in the right temperature range, which is about 20 to 30 degrees. Now, when to cool it down, it's obviously everything depending of the cell size. Is it small? Is it large cells with chemistry and so on? It's all about dissipation. Where are the tabs allocated and so on? So that are very key parameters to define how it should be done, cooled down, in which way and so on, and which techniques can be applied. So it's also a matter not only of technology, but also of the integration which are associated to that. And typically there are three ways to do the cooling: by radiation, you cannot change too much, by convection, and by conduction. And typically the conduction is the most efficient way, as you know, where you have like the cooling plate which is connected to the battery and it's removing the heat. There, see the formula which are associated to that, which are indicating the surface area is something very important, and the medium that are related to that. So for convection, as I said, it's a good one, but not ideal one that you should know. The free convection is quite still limited, and it's also caused by natural or forced convection, which is typically air. Heat dissipation conduction is the most optimal one, as I said, where you have a connection with another medium to remove the heat. And typically, we are speaking about direct cooling or even cooling plates. How does a cooling process looks like? It looks like following. We have pump, a battery, jacket, and radiator. Typically, if you take just a simplified cooling like the ones that you see here and Renault Zoe, that could be done. That's possible. That could be applied. But you have also very complicated one where it's based on two steps, where you have the condenser, where you have the evaporator, where you have your chiller, you have your cooler, and so on, which can do the both heating and cooling at that moment, etc. And that is more sophisticated and also heavier, which require also more volume. But you have to look to the numbers here below. Free convection has a typical heat transfer coefficient about 50 to 3000, and just forced convection water in liquid has something between 50 to 10,000 watt per meter square Kelvin. And there's a reason why liquid was the first choice for many car manufacturers where they are operating in different environmental conditions. If you go to Japanese, they are using only air cooling. Europe, US, they are using the liquid one. If we take the Tesla one, you have typically the modules, and between two modules, typically you have such flexible cooling plate in between where the fluid, which is a glycol coolant, is going through and it's removing the heat accordingly. So that's typically Tesla pattern and approach for that. Another one, Audi, e-tron. So they have typically here large cooling plates, as you can see here, large cooling plates, which goes over the full modules that are integrated in the battery pack, and that is which is supporting the cooling of the battery in a proper way. And for your information, we spoke the last time about here. You see here is the battery housing where the battery modules come. This is a cover in aluminum, and you see here even they are integrating aluminum crash structure on top in the case that a crash will come, that this structure will absorb as much possible actually the impact of the crash on the battery pack. You see, this comes here in between to have a robust structure as much as possible. And that is the lower protection cover. And here is a battery frame. Now, for Bmw I3, you see that is a battery housing, and that is a big cooling plate which are placing on bottom, and then the modules are coming on top. Ferrari is using 120 kilowatt hour battery pack, and they are using also liquid cooling, as you can see there. Liquid cooling between the modules, which is based typically glycol, that is based on glycol mixture with water 50%. Immersion cooling, explained that before, is typically where you have a direct contact between battery cell and the electric liquids. And there is a typical one, it should be heated. You have electrical heater in the winter, which it's warm up the electric liquid, and then the heat can be transferred to the batteries. But when it should be cooled down, yeah, what is happening typically, this becomes warm, the liquid becomes warm, it evaporates, it comes in contact with condenser plate, which it removes the heat accordingly, and it goes down. But this process is never perfect, it's never equal, because what is important, the level of the liquid should be perfectly equal, which is very difficult in a vehicle. Secondly, the evaporation is not happening perfectly, so you create gases and so on, and the sealing is also a very difficult matter. If we speak about immersion cooling, everything is about which types of liquid are you using or medium, and there are different types. Here you have the 3M Novec, which is very important, which is most used one, but we have also the MyVolt, which is also something that can be used, and I believe here the most important is the liquid density. So take here the liquid density of this one is in the range of 1,400 gram per and if you take here the same for this one, it's much lower. So it's much heavier, it's much more attractive for in application. And that's also one of the design parameters. Immersion cooling, we know it's interesting, but it's actually going to contribute to the weight requirement. And anyway, immersion cooling challenge is the fact that it's 3 to 4 times heavier compared to classical cooling plate with cooling plates. It's also more expensive because it's not widely used in mass production. Pressure should be regulated. Need for adding fluids, because I said the process is not optimal. You get here evaporation, which doesn't translate afterward back in a good condensation process. Second, lastly, it is also requiring perfect sealing. So the maintenance by adding fluid and also perfect sealing, or by repairing the sealing, is also requiring a lot of maintenance, and that is the big challenge. Direct cooling can also happen in different ways, depending of the architecture and the concept of your battery system. How you look to that, is that longitudinal way or the bottom-up way? And also, it's important to you to know which type of cooling media are you going to use. Is it the electric? Is it oil? And it's going to have huge impact on the parameters like required flow, volume flow, pressure drop, and GWP, which stands for global warming potential. But what is more important is that direct cooling doesn't need any thermal resistance of gap fillers between the battery cells. When we use cooling plates, of course, contrary, that means you need cooling plates or in bottom where you have make connections between the cells, or for out cells, you have actually cooling plates between the cells directly. So it's different configuration, and it depends actually how your configuration of battery modules is, what type of battery cells that you are using. Refrigerant cooling is another process where typically, if you look to a classical liquid cooling process, where you have condenser, evaporator, compressor, chiller, pump, etc., and a lot of pipes and valves. For refrigerant cooling, it's a different method. You have condenser, evaporator, compressor, similar like this one, and that's all. And that's all. So the process-wise is much easier, but of course the level of pressures are also quite different. but the cooling efficiency is not more higher. But what is important to know when we speak about refrigerants, we speak about also different types of media for refrigerant, and that is what is indicated here. And what we should know, that we have a parameter which we call it GWP, global warming potential, and not every refrigerant media is environmental friendly. The higher the value, the worse it is. The lower the value, the better it is. So from that perspective, typically a standard refrigerant, we know it is R134A, which is what use, but yeah, it has high GWP. So ideally, we should be in this area. And if we want to have a better cooling, we should go to there. So, and that's creating opportunity, but also a challenge in that regard. So GWP should be less because there are regulations are happening and that are interesting refrigerant media. But if you want to do still more better, you should go to there. But that means also you are increasing pressures from few bars to 100, 150 bars. And that's creating a lot of challenges and problems at such a moment as a system and what actually are related to that. And that is what we can see here. The global warming potential for R744, it's typically this one, yeah, compared to this one, sorry, is here it's 1, and here it's around 1,430. It's very problematic. However, saturation pressure is something very big here, etc. So there are different pro and cons that you have to take into account, which is actually, it's not easy to handle that. R744 operates on pressure 10 times higher at least than the classical one. And that's require a lot of engineering work, optimization work, and particularly regarding the safety and selection of the component. And this slide, it illustrates actually everything. And what is illustrating is the fact that if we go to the novel media here, you see that it's very expensive. It is this one. It's very expensive. It needs a larger compressor, larger pipes. It needs also a lot of safety, special joints and sealing. And however, for the CO2 R744, it needs completely novel compressors and completely qualified people that should work in that. And that is not an easy exercise in general. And typically, automotive industry is very, let's say, conservative industry in that regard. So you have to take that into account, that the choice or direct change to that will be quite not happening immediately. But we see also happening often for fast charging applications is the ones of Rimac, where they integrate a combination of heat pipes with phase change material. What is a phase change material? It's a material which is integrated in capsules, which can change from phases. It can become from solid to liquid, and from liquid to solid, depending if it is absorbing or releasing heat. And what does it mean? It can facilitate the thermal management in one or another way without having additional active components. However, it is, as I said, it's changing from phase. If it's becoming in the liquid phase, it cannot take further heat up. So it's working just in application where heat should be fast absorbed and should be released also very fast, etc., but not for long-term heat absorption. And that is, it was creating a lot of interest Heat pipes is also a passive component, as you know. It's where you have a heat source and heat sinks, and by circulation of fluid, it can go in the evaporation mode, and then based on the contact with the condenser side, it goes back in the liquid phase. That is something interesting which can facilitate that, and actually that is heat pipes is nothing new. It has been used for many years in the laptops field, and it's all about materials. So you see here the thermal conductivity of many materials like aluminum, diamond, copper, and you see the heat pipes have higher thermal conductivities, and it's a potential solution, and Rimac is using that where they are charging their battery at 100 kilowatt without any liquid cooling. Then heat pipes, you can use it also in different ways. Here you have conventional ones where you have here such shape or in such shape or such shape, depending actually how you want to integrate that in your application as such. Then what does it mean? That means it can be integrated in a such way, heat pipes, or it can be integrated in such way, or it can be integrated like this one and like this one, depending how you look to it. But also heat pipes can be also integrated with a phase change materials, for instance, to increase the performances to such extent, but it will also increase the weight that you have to take into account. What we typically also have in electric vehicles is waste heat recovery. We have a lot of waste that we are releasing, which is not providing any added value to us, and that could be waste from batteries, or that could be waste from electrical motors or inverters and so on. What is actually could be happening to increase the energy efficiency is also to recuperate the waste of different parts in order to use that afterwards for heating or for cabin, etc. Here you see an application of Kia Soul, how they typically use cooling. So they have typically air from a HVAC system. It goes into the battery, it starts cooling the battery, and the warm air, they take it through a ventilator to outside. That is typically the process that is happening in that regard for Kia Soul. As I said, the Japanese are typically using air cooling. Tesla Model S is liquid cooled, as I said, large modules, and where you typically have condenser, evaporators, and etc., which is regulating the full concept, but it's also integrated with a radiator. Why? Because not each time you need to activate the compressors and so on. You can even in slow mode, you can use already the thermal management from the radiator. It is more sophisticated how Tesla concepts looks like. You have compressors, you have condensers, you have a chiller, you have a lot of pumps, expansion tanks, etc., etc., etc. Audi e-tron, you see here, you have here a large battery integrated with what we have also here for Tesla, compressor, condenser, radiator, chiller, blah, 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 blah. And then depending in which mode you are, in which conditions, the thermal management controller is taking the right decision. Here, battery charger and battery cooling are done via a chiller. Typically, you are charging, and then the battery is doing that through a fast way, which is through a chiller. Here, battery cooling is happening through a chiller. See here, a chiller is cooling down, and the heat is taking off. And battery cooling via low temperature circuit, which is the low temperature circuit. The conditions are not very heavy, is a radiator, and so on. So it is the cooling of a battery. It's not only selection of the component and strategy, but also of the thermal management strategy, which is applied on that. So it is quite complex topic, but I was willing just to illustrate based on a couple of examples how possible is to deal with that in that regard. Are there any specific questions before moving to hydrogen?
You have any questions on related to thermal management? I think that you have made a very interesting summary of all the techniques and all the strategies that for the thermal management. I don't know if no more questions. No questions. No, you can
Good.
with the hydrogen.
We can move to hydrogen. So I want, before starting, to tell you one thing. Hydrogen is not in competition with battery, and battery is not in competition with hydrogen. They are both complementary to each other, and they fill each other depending on the application. But before moving to that, we should know what is hydrogen and how it's working. So typically, hydrogen is actually based on when you combine H2 with O2, you get electricity, and the output is H2O. So that is water, typically. That is what we call it fuel cell working, which is providing electricity. It's very simple from conceptual, but it's very difficult from optimization point of view, etc. What is important to know, hydrogen can be as battery, green, blue, or gray, depending actually how from where you are taking the energy to create hydrogen. And typically we are classifying hydrogen in 3 categories. Green hydrogen, where the energy completely is taken from renewables. So green hydrogen is an electro fuel, a high value energy product created from low cost renewable electricity. We have blue hydrogen. What is blue hydrogen? It's a product with CO2. There's some still CO2 popping up, coming out of that, but the CO2 could be captured and sequestered or stored permanently in a number of ways that are being researched. So there is some amount of CO2 is still produced, but it's still not so heavy. It's still small amount. What is gray hydrogen is from steam methane that can be produced, which emits actually 7 grams of CO2 in the atmosphere for every kilogram of H2 produced. So take that into account. Depending here, nothing of CO2 is produced. Here there's so small, and here there's a maximum of 7 kilograms of CO2 per kilogram of hydrogen. And that's a problematic. Here, not good solution. Here, still acceptable, and that's what we want to go ahead with that. Now, for fuel cells, we can only use pure hydrogen and nothing else. Regarding applications, of course, trucks is a very a key application there. Why? Because hydrogen can be used in trucks in a 2-way. Or you inject directly hydrogen in your internal combustion engine, or you use hydrogen as a source of energy for a fuel cell. And that's what you see here. You have typically here a hydrogen tank. Yeah, you have here a fuel cell system. And for people which doesn't know, and that's why we say batteries is not in competition with hydrogen. Hydrogen is good to deliver energy, but not to deliver power. So here, battery is foreseen to deliver the required power, where we combine energy by power, and that is actually high power units. Another application is an electrical bus. In Belgium, here you see the hydrogen station, here you see a bus. It is based on the same principle, not more and not less. Now, what is interesting from that perspective, that hydrogen can be filled in quite very fast, in a couple of minutes, which can be filled in, and you go and you have actually the same functionalities as you have for a conventional vehicle. And then we see from that perspective for electrical buses based on how fuel cells is slowly growing. It's not on the same level as in battery electric buses, but slowly is growing. And this is the landscape that we see in Europe. It's not so huge because it's still new technology in that regard, but it's popping up more and more. Another aspect is marine applications. Marine applications is, carrying tons batteries is sometimes quite for large vessels very difficult. That's why hydrogen is a very interesting technology from that perspective, and in particularly when you can inject it directly in the internal combustion engine. Another application, stationary. Now you have to take into account that hydrogen production is a factory, it's a chemical plant in that regard, and it can be used from different way, where you can send it to a tank, and tank can fill a different type of application, but it can be also hydrogen easily can be stored. It can be used for cooling or heating, or it can be used for power to gas or for energy development. So hydrogen has quite a lot of upscalability and interesting conversion mechanism to be used in different industries. However, everything is about efficiency. If we take an electric battery or vehicle, whatever, and we take the energy from renewables 100%, and we convert that until the electrical motor efficiency, we see that the overall efficiency is around 77%. Let's take to hydrogen. If we do that, it's 33%. So you see, we are losing a lot of the efficiency when we are converting hydrogen from renewables directly when it comes to the wheels. And the biggest problem is actually the electrolyzers. Here is the biggest problem that we have compared to this one. You see here, it's 94%. Here is already 68%. Power to liquid is a disaster. Power to liquid petrol, it's another disaster. We have to take into account, okay, hydrogen is creating flexibility, but hydrogen efficiency is also not very high. And this is also demonstrated here. 100 kilowatt hour you take from renewable electricity, and then you convert that to electric vehicle. To the end, you get 69 kilowatt hours. Take here, for instance, 100 kilowatt hour electricity generation, and you see through the conversions, you are losing a lot of energy. And then there are different ways, or you are doing H2 compression, and then you are transporting that, and then you are converting to fuel cell and electric vehicles. What is remaining? 23%. If you do that liquefaction to make hydrogen liquid at higher bars, and then transfer it, you get 19%, 19 kilowatt hour. You see, we are losing already 80% from that perspective. And that's also what is presented here. If you take electric one, 77%, and WTW is meaning well-to-wheel analysis. For a battery is, let's say 62, depending from where you're taking. Hydrogen 29, and power to gas is 20%. So the choice for long range, long haul is still, from my point of view, is still above 500 kilometers for trucks is hydrogen, because you have the flexibility parameter. And for medium regional trucks or city trucks, whatever, or buses, I believe it will be more dominated by the batteries side. Now, what is the problem of hydrogen? The problem of hydrogen is actually not the technology itself, it's a cost of hydrogen itself. Due to the low efficiency, hydrogen cost dollar per kilowatt hour is very expensive. Typically it comes to a value which is close to 10 euros per kilogram hydrogen. And that is something very difficult. The target is that it should come between 1 to 2 euros per kilogram hydrogen. Otherwise, the business model, it will be very not attractive and very difficult to obtain. And that is what we see also in this graph. We have, consider you have a fuel cell electric truck and battery electric truck. And we see to the total cost of ownership, or what we call TCO, is for battery electric truck 353,000, for an hydrogen is 437,000 euros. So total cost of ownership is very heavy. Even in the future, the difference will remain, but you have also to look to another parameters where charging refueling time is very short compared to the battery one. So it depends of the operating scenarios, depends to what you are looking to it, and you can make the right choice. And that is, for instance, which is representing the regional delivery trucks. If we go to long distance trucks, we see actually a difference here, which the difference is becoming not so tough, quite small. But since this parameter is very important for such types of applications, this will be a no-go in any way. If we go further, here again, which is summarizing regional delivery and long haul, we see that solutions for long haul will be more fuel cell or hydrogen oriented to such extent, because the energy consumption maybe is still high for hydrogen compared to the battery, but the flexibility what we have there is much higher than for the BV. And here for the regional delivery, the total cost of ownership is much more important. And the same here, when you look to the cost, leverage cost of energy for electricity are the values. And you see here the cost for hydrogen, it is like that. What is important to know, it's also to know from where are you taking the energy or the electricity which is produced. If you take it, by the way, from Europe, that is what you are going to pay, 17 by 2030, 15 euro cent per kilowatt hour. But if you take it from North Africa with cheap electricity that they are taking from solar PVs, it is about 6 to 5 euros cent euros per kilogram, and that is actually making the things very interesting. That it is interesting to produce that from African countries. Another problem is the infrastructure. The number of infrastructure for hydrogen is very limited, and that's creating a lot of problem. One of the ways to do that is to convert conventional fuel stations more and more to hydrogen, and this process is also ongoing, but it's not going to happen by tomorrow. That was my last slide for second session. I was again willing to give you an over picture. The message that I want to give you: nothing is black or white. Everything is white and everything is black depending how you look to it. And everything is application dependent. Is it fleet or not? How do you operate that, and so on? It's very important. Just to give you an example, for an electrical bus, every minute that you don't operate, it has huge implication on the TCO. So there, hydrogen can create quite a lot of flexibility, because we know that the charging time of batteries is long. And it's the same for long-haul truck, because the big part of such type of application, long-haul truck and electrical, let's say, buses in the cities, of public transportation buses, is a driver. So and the 50% is just a driver. So it's more dramatically. So every minute they are standing, not driving, it's increasing the TCO, and hydrogen can create a lot of flexibility from there.